Okay, so this is going to be something like speed, not necessarily like velocity, because velocity, if you guys have taken physics, generally has direction, speed doesn't, right? So chemical kinetics is going to be looking at the speed of reactions, right? And generally, when you're looking at a time-dependent quantity, how do things change with time? You're looking at some property changing. So with the speed, for example, you're looking at the distance from some point that's changing with time. With kinetics and chemical reactions, generally what you're looking at is the concentrations, how concentrations change with time. And so just by looking at how concentrations of things change with time, we can determine a lot. And one of the big things that we can determine is the reaction mechanism. How does this mechanism actually happen? And so you also might ask, well, how do we look at how the concentration changes with time? We'll talk a little bit about the different methods that you can do that. Generally, you're looking at some other properties. Measuring something directly through concentration is pretty hard, right? It's hard to count all the different molecules that exist within a certain volume of solution. And does anyone remember how we denote concentration in chemistry?
Molarity.
Molarity, right? So this is going to be units of concentration, has units of molarity, which was symbolized by what symbol? Capital M, right? So that would be capital M. And if we were looking at the concentration of some species, I don't know, some arbitrary molecule. So especially in second semester Gen Chem, we're going to be using a lot of arbitrary reactions that are happening. So for example, we won't use a specific chemical compound, but we might show a reaction that looks something like A plus B goes to C or something like that. How would I symbolize that I'm talking about the concentration of A? All right, this is just a fancy way of saying, if we have y equals mx plus b, x is our variable there, and maybe that's distance or something like that. Generally for concentration, so the concentration of A is equivalent to just writing the brackets around A. Right, if we write the brackets around A like that, in chemistry what we're referring to is the concentration of that species. So if we were to include the units of molarity, we could say the concentration of A is equal to 1.0 molar, for example. Right, so that's a numerical value. The units of molarity, and what are the units of molarity? Like what are the actual, so fancy words, what are the dimensions of molarity? What is molarity? Moles per liter, right? Molarity is equal to moles per liter. And what is a mole of something? So I know it's maybe been a while. How many of you have not taken chemistry in 6 months or a year? I'll say. How many just took your last chemistry class recently, in the spring or the fall? Okay, so most people are fresh, right? So, all right, so moles. What is a mole? A mole can be a certain amount of anything, right? It's like a counting device. A mole just tells us, the same way we say, if I said I had a dozen bats, that means I have how many bats? 12, right? So a dozen eggs, that's 12 eggs, right? A mole is just, if I have a mole of something, I just have 6.022 times 10 to the 23 of whatever it is, right? So molarity is just that number, 6.02 times 10 to the 23 per unit liter of volume, right? So that's how we define concentration. And in kinetics, we're generally looking at the concentration of species changing with time, right? So the rate or how fast these concentrations are changing. And that lets us study then tangentially or directly the different reaction mechanisms that we can have. And so what does that mean of different reaction mechanisms? Does anyone have any idea what a reaction mechanism is?
Is it endothermic and exothermic, or is that part of it?
So that is related to reactions, right? Because that tells you the relative energy difference, and that's actually an important distinction, right? So kinetics, we're looking at time varying things. When we look at things like endothermic or exothermic, That's actually in the realm of thermodynamics when things are not time varying anymore. But to understand that, you have to understand, that's a specific case of the kinetics. And so there can be multiple reaction steps, which would be the reaction mechanism, and each of those steps can be endothermic or exothermic. But the reaction mechanism tells us specifically how do we go from A plus B to C. Is it one step that happens, or is there an intermediate, where we create some other complex before we finally get to our product? So somewhere that you see this quite a bit would be in biology. We have catalyzed versus uncatalyzed reactions by enzymes in your body. And so those introduce a new step, right? Because if we have a reaction, and we'll talk more about catalysis and stuff in the next coming weeks, are we just going directly from A to B to C? Or are we gonna have, if we add a catalyst or something, plus some enzyme where we get some complex with the enzyme A, B, and then we get to our product C. Something like that, right? So this would be a one-step mechanism, and this would be a two-step mechanism. Also, I know my handwriting is not the best, so if you can't read anything or if something's hard to see, don't hesitate to stop me or have me clarify anything. And so through the study of kinetics, or how concentrations are changing with time and how fast these reactions are happening, you can determine reaction mechanisms. And you guys will be very familiar with that in a couple weeks. Oh, and how to do this, change the view. Mirror, presenter sheet, interface and Zoom. Okay, there we go. Okay. Any questions on that? No. All right, so what are some factors that affect the reaction rates? Well, the concentrations of your species, depending on the type of reaction. So this is depending the type, and I'll put to preface the order of reaction. If you have different concentrations of your species, that means that reactions will tend to happen faster. For example, if you have a buildup of a bunch of reactants, then you're probably going to start forming products a lot faster because you have so many reactants available. A lot of times kinetics is due to just random chance of things being close enough to each other to actually have things happen. So if you have everything you need to happen, and that's all you have, then everything is inherently already close to each other, so those reactions are going to happen faster. The speed of that reaction will happen faster. If you have, not that many reactants, the chance of reactants coming together to find each other is a lot smaller. Just based off ideas of, one molecule's here and the other one's at the side of the room, the chance they'll find each other to react is low. Whereas if you guys all represent all the molecules at the beginning, you guys are all reactants, you guys are already next to whatever you need to be to react to form products. So concentrations of reactants affect the reaction rates in the kinetics of the reaction. The presence of a catalyst also affects the reaction rate. And so I believe you guys talked about catalysts in first semester chemistry. Does anyone remember what a catalyst is? It's related to the speed or kinetics of a reaction. Does anyone have any idea what a catalyst might be? So when even in popular culture and stuff, you say, oh, this is the catalyst for some event. What does that usually mean?
Does it speed up the reaction?
Yeah, catalysts work by speeding up a reaction, right? So there's something that speeds up a reaction. So in popular culture, for example, you say this is a catalyst for an event, meaning that's what started that event, right? This is what made the event start to happen. A catalyst often works just by making sure two molecules are close enough to react, right? So like an enzyme takes one reactant, puts it next to another, reaction happens. So it works by speeding up a reaction. And generally the way that it does that is it lowers what we call the activation energy. And that's usually symbolized by EA. We'll talk a little bit more about that when we get to the Arrhenius factor. But it lowers the activation energy, so activation energy, as the name suggests, is just the energy that it takes for the reaction to happen. So if you lower that energy, the reaction happens faster. Okay. You guys a second to finish, right? All right, so some other things that affect it. Temperature, right? So how do you guys think temperature will affect?
Usually hotter makes it go faster.
Mm-hmm. That's exactly right, right? So generally, the warmer a reaction, I'll put that in quotes just because it's kind of a simple way to say that, the faster a reaction will proceed. And so the temperature, means actual temperature of the molecules in the reaction can go up. In general, what we're saying is that when we add energy to a reaction, the reaction happens faster, right? So in the lab, as you guys have done in the past, what's another way that you kind of add energy to a reaction? Bunsen burner, right? At Bunsen burner, you're adding heat directly, and so that transfer of heat causes the reaction to happen faster. What's another way, maybe without directly changing the temperature? For let's say you have sugar molecules or sugar crystals, right? You want to dissolve it in water, right? That represents a reaction. You're going from the crystal sugar phase to the aqueous, right? Aqueous just means surrounded by water. So you're going to the aqueous sugar phase, right? How do you get that transfer? Yeah, you just stir it, right? So you're adding energy by adding, kinetic energy. You're making the molecules move around, and that causes the reaction to happen faster, right? That's why when you have, you want to dissolve sugar in coffee or whatever, generally you stir it because it makes the dissolving process happen faster. And then also, if anyone has ever gotten sugar in their iced coffee, what generally happens? Yeah, you get a big old clump of sugar at the bottom, right? Because the reaction is cold, so it doesn't want to dissolve as fast, right? So temperature definitely affects how fast a reaction can happen. The other thing would be surface area orientation factor. Orientation factor is just a fancy way of saying, are they in the right shape for the reaction to happen? Surface area is another thing, right? If you have a large amount of surface area, the chance that you'll meet another molecule will be a lot larger, right? So generally things increase with surface area of molecules or whatever the substrate it is that they're looking at, right? So the larger the surface area, the faster a reaction happens. And so an example of this is for electrodes and electronics, or when they're kind of doing state-of-the-art testing for using voltaic cells, which you will be going into later in the semester. Traditionally they use like a copper or silver cathode or anode or something like that. But then now a lot of times they're using what's called graphene, which is a specific form of carbon. And graphene has what we'd say a nanostructure, right? And as things get smaller and they make more shapes at the smaller scale, the actual surface area starts to get larger, right? Because you can imagine if you had a cube, right? And then on the cube, you have the same volume, so you shrink the size of the cube, but you make little cubes that come out of each face. Now you've added all these extra faces, the surface area goes up. So the surface area, the reason they do that is because then a redox reaction, which you guys may have heard of in Chem 1A, a redox reaction can happen faster because the surface area of where it's happening is increasing. And again, the orientation factor, so one way you can visualize this is if you have complicated molecules, and let's say you have two molecules that look like this, and they need to be in this orientation for a reaction to proceed. Versus something where you have, let's say, just two spherical molecules, and they need to be in that orientation for the reaction to proceed. these you can rotate, spin them around, they can come from any angle, right? And the reaction is still going to happen because it's two spheres that are interacting with each other. So this would have a larger orientation factor because you're not as restricted for the reaction to proceed. Whereas something like this, these two have to be facing each other. If you think in 3D, they have to be facing, you know, in the same plane as each other. They have to be facing in this correct orientation. If they go this way, the reaction will happen. So that's going to restrict how that reaction happens a lot, which means that the speed of that reaction should go down. So this is kind of trying to give you guys an intuitive sense for how reaction rates are affected by things like surface area and the orientation of these molecules. Okay. So these are kind of not heuristic, but they're things that you may be familiar with in seeing exactly how those affect the speed of different reactions. And a lot of times in this class, we say reaction, we think of chemical reactions, molecules coming together to react. But again, this can also be represented. A physical process can be represented. We go from a gas to a liquid, for example. We go from, crystal to something that's solvated or in the aqueous phase. So reactions can represent a lot of different things. For example, in protein foldings, so the guy who won the Nobel Prize last year developed an algorithm to see how proteins fold, right? So to predict the structure of proteins. You can even represent a protein folding with a chemical reaction because you say, okay, we have multiple steps that we go through. Well, I can just say this is the initial state, the second state, and the third state, and we have a chemical reaction that's going between each of these states. It can refer to a lot of different styles of change, or you can use this formalism of kinetics to understand a lot of these different things. So this will, extend beyond just chemistry or reactions between molecules. Okay, any questions? All right, so then we'll actually talk about reaction rates. And so the reaction rate is usually represented, so there's going to be a lot of different variables we use, not a lot of different, I should say, a lot of the same variables we use that represent the same different things. So the reaction rate is represented by an uppercase K, and it is going to be the change in concentration per unit time. So what would be the units if it's in concentration per unit time? Yep, it would be molarity per second is how a reaction rate is always going to be defined. And the reason I'm kind of emphasizing this is because when we talk about reaction order and stuff, there's going to be a constant, and you can always, without memorizing, determine what the constant is by just remembering that the reaction rate is going to be in units of molarity per time. And similar to how velocity or speed is determined by a change in distance over a change in time, a reaction rate is looking at a change in concentration. So I'm just going to put something like delta M over a change in time. How fast is the concentration of a species changing with respect to time? And so this, if you guys are mathematically inclined, or if you guys have started to take any calculus classes, is kind of what a derivative eventually looks at, right? You look at the limit where this change in time gets very, very small. We don't have to worry about calculus for this class, but I'll introduce it as we go along for those that are interested. And so reaction rate is always similar to a speed going to be a positive quantity. All right, so since it's a positive quantity, we may have to adjust what a reaction rate looks like, because if we're going from reactants to products or products to reactants generally have direction, but reaction rates don't. Same way that velocity has direction, you can have a negative velocity, but you can't have a negative speed. Okay, so that's how we define a reaction rate. And like I said, because reactions have direction, a reaction rate can also be defined as K equals minus the change in concentration, and this will be represented by a reactant, in this case, over a change in time. right, we have to add this negative sign here, because when we use, so let's say a negative sign added, because when we use this symbol, so I should have probably mentioned that before, delta, what does delta mean? And these three lines here just mean defined as, or the definition of. What does delta mean when we use it in physics? Or, the difference, right? So this is going to be the difference in a quantity. And generally, it means whatever the final is minus the initial, right? So if we have an example, delta t is equal to t final minus t initial. And this would be like for temperature. So this is temperature, for example. In the concentration, we're saying the initial concentration, or the final concentration minus the initial concentration. So just by looking at this expression right here, if we have minus, this will be the concentration of our final minus the concentration of our initial over T final. So this is the initial time minus, or the final time minus the initial time. All right, if we're looking at something like a reactant species, then the initial is going to be higher than the final, right? So this, what should the sign of this number in the parentheses be then? Right, this number is larger than that number. It should be a negative number, right? We're taking a small number and subtracting a larger number. Like 1 minus 2 should give us -1. But since the reactant rate always has to be a positive quantity, that's why we have a negative sign here. So what you'll see is that for reactants, the reactant rate is going to have a negative sign, and for products, it's going to have a positive sign. And then, based off of convention, this can always be flipped around, just depending on which way the reaction is moving. But yeah, so we'll see a lot of deltas, especially in kinetics, and that's what this represents. So I know I write a lot of variables here, generally, more algebraically inclined, so I like to leave everything in terms of, the variable, and then I plug in the numbers at the very end. If you were working through problems and stuff, and you want to use your numbers all the way through, that's fine too. But if everything, and if anything is confusing, let me know. I can clarify. Okay, so how would we see reaction rates in a plot? Well, if we have something, let's say we have a reaction A, and it's just a simple reaction where we just A just goes to B. All right, so we're going to use a lot of kind of symbolic reactions here, because otherwise you guys will probably get very tired of seeing hydrogen gas plus iodine gas goes to 2 hydrogen iodide. All right, so we have, this is our symbolic reaction, and we can have in 2 colors the concentration of A, and in blue we'll have the concentration of B, and we'll look at how they change with respect to time. So if we start off with all of A, what should the concentration of A be higher or lower than B at the initial time? Low. If we start off with only A, right? If we only have A, then that means that concentration should be high relative to B at the beginning of the reaction. All right, so A, let's say we start, and I'll put it directly on the line. We start all the way up here. And let's say we start with 0B, so B is going to be all the way at 0 down here. As the reaction proceeds, and it's only going in one direction, what should happen to the concentration of A? It decreases, right? So the concentration of A decreases, and we don't know exactly how it's going to decrease. We're going to talk more about that later, but it should go down, right? And as the concentration of A is going down, what's happening to the concentration of B? it increases, right? So B is going to be going up. These are how the concentration should vary as time changes for the reaction, right? As the concentration of one species decreases, the other one increases depending on the direction of the reaction. And so how would we see the reaction rate on a plot like this? Well, the reaction rate was defined as what again? The change in what over the change in what? Change in concentration over the change in time, right? So that means that we're going to have some interval here, and I'll use a different color. I use purple, for example. And let's say this is our initial concentration. And so usually when you have a 0 here, that just means the initial concentration. And then we'll say this is our final concentration of B. So this quantity here represents the change in the concentration of B. And then the quantity we have here, this is going to be our final time, and this is our initial time. This represents the change in T, right? And so when we take the ratio of those, we have delta T, delta concentration of B. That is defined as our reaction rate. Does anyone see what else this, or does this look familiar to anyone else in any other context when we're graphing or plotting stuff? It looks like the slope, right? So this is also equal to the slope of the concentration versus time curve, right? And depending on the type of reaction we have, we see that the slope, which just represents the line that kind of comes tangent here, as the reaction proceeds, the slope changes, right? Which means that the reaction rate changes as time changes, which is what we would expect because concentrations are changing. So we kind of have like this feedback loop where the reaction rate changes because of time changing for certain reactions, right? For other reactions, it could not change. And we'll talk about that a bit. But this is how we see the reaction rate when we're looking at plots of concentrations versus time. Is we have, it's represented by the slope, right? And we see that because just the change in concentration over the change in time. Yeah, if you guys need to take a photo or anything like that, you can always just let me know and I'll pause. Like I said, I'll also be uploading these notes, as we finish them in class, I'll upload them to Canvas. I'll usually upload them on the modules right under where the notes are posted. So this is Kinetics Part 1. Once this is completed, I'll post, Kinetics Part 1 completed right under that. All right, so we've been here for like an hour. Let's take like a 10-minute break. So at 9:40, we'll come back and we'll continue talking about the first part of kinetics. This is how we see reaction rates on a plot, and this is kind of how, when people do things experimentally, this is generally what they're looking. Generally, you're not measuring the concentration directly, it's through some other tangential method, but you're looking at how does the concentration of something change with time. And so, generally, you can look at the change in concentration of a species. You'll have some data tables, so especially for the first couple of months of this course, you'll probably be given a number of problems, or we'll go over a number of problems together, where you're given some change in concentration with respect to time, and then you can determine, or should be able to determine stuff, right? So this is just a, representation in a table of the same thing that we plotted on the previous page, right? This is just how is the time and the concentration of all the species changing. To get these values let me go to the laser pointer. In this column right here, all you're doing is you're taking the final time minus the initial time, and that gives you the change in time over that interval. And then the interval, we're looking at evenly spaced intervals here. This could be 10 seconds for each of those. And then the ratio of those gives you the reaction rate, right? And that's the instantaneous reaction rate, right? Because you're taking between two specific points. You can look at how the reaction rate changes continuously, but that involves a little bit more calculus to do something like that. And if we're looking at something where this was a reactant, how would you know that this is a reactant or a product in this case?
Because the concentration's getting smaller.
Yeah, the concentration is getting smaller. Smaller, so that implies that this is a reactant in the reaction. The other way is if you see the rate, we have a negative sign there, right? Because the reaction rate always has to be what kind of quantity? A positive quantity, right? So this always has to be a positive quantity, so we also have the negative sign included there to make it positive. Yep, so that's how that happens. So you don't have to draw this whole table. So reaction rates generally decrease as the reaction proceeds, and that's because the concentration of the reactants they're decreasing, right? And as the concentrations decrease, the rate should decrease. And I'm going to put generally decrease because depending on the type of reaction, that can be different. And another thing is that since the reaction rate represents this entire reaction happening, we should be able to represent the reaction rate as an expression that of the concentration of any one of these species in this reaction, right? So we should be able to express this for any one of the species, meaning that the concentration of H2 gas should be proportional to the change in concentration of I2 gas should be proportional to the concentration change in hydrogen iodide gas. And so this symbol right here, that just means proportional to, right? The rate of formation or depletion of each of these species won't be exactly the same, but they should be somehow related. Does anyone have an idea how they might be related if we're looking at a chemical equation? Right, if we think about for every 1 molecule of H2 we lose, how many molecules of I2 do we lose? 1, right? Because there's one of these reacts with one of these to create how many of our hydrogen iodides? 2, right? And so that's probably this proportionality is going to be related to the stoichiometric coefficient there, right? So stoichiometry is going to come into play here, and that's how these are going to be related. And stoichiometry is a big word and stuff, but really all we're doing is we're kind of just counting, counting for each reaction that happens. We have one of these reacts with one of these to create 2 of these, and that should affect the speed of things, right? Okay, is anyone still writing? Okay, I'll give you guys any questions? And so if we look at each of these species individually, the rate of disappearance of H2 is going to be equal to the change in concentration of hydrogen gas over the change in time. The rate of disappearance of I2 is going to be the change in the concentration of iodine gas over the change in time. And similarly for hydrogen iodide, it'll be the change in concentration of hydrogen iodide, right? And so this is one of those things where it's important to look at the verbiage or what words are being used here, right? Because we're not talking about a reaction rate in this moment. We're talking about how the rates of disappearing and rates of formation are going to be related to the reaction rate. So this is saying, what is the rate of disappearance of H2? Well, that's just the change in concentration over the time. Rate of formation of HI is just a change in concentration over time. But if we want to relate these to the reaction rate, that's where we have to say, okay, we have to think about, is it a reactant or a product? So is it going to be negative or positive to make the rate a positive quantity? And then also, how is stoichiometry going to affect those, right? Because for this entire reaction, we have a single reaction rate. For each of these species, we have a different rate of formation or rate of disappearance for each of them, right? Because the reaction rate is just looking at overall the speed of this reaction happening. What we're looking at here is, well, how is the change of this species? What is the change in the concentration of just this species? And the same thing for I2 and HI. And so how are these going to be related to the overall reaction rate? And so the rate of formation of a product, again, is always going to be the change in the concentration of the product over the change in time. And the rate of decomposition or depletion of a reactant is going to be the change in the concentration of whatever the reactant is over the change in time. Except since this always has to be a positive quantity for the reactant, we have to put what?
Negative sign.
Negative sign. So this is going to have a negative sign there. And that's because, again, we're thinking that each of these is a specific reactant or product in the reaction that we're looking at the change. And we want to relate this to the speed of the overall reaction. How fast is the overall reaction happening? Okay. Am I good to go on to the next? If I'm moving too fast, let me know. All right. So how are we gonna relate this? Well, let's say we're looking at relating the reaction rate now to the rates of formation and depletion of each species. If we want to see the rate of decomposition and relate that to of H2 gas and relate that to the rate of formation of HI, how would we relate these two? All right, so this is similar. For each time this reaction happens, right, we have one molecule of hydrogen gas, and it forms how many molecules of hydrogen iodide? 2, right? So what would you say if you're creating one twice as much, how much faster do you think that reaction is happening? 2 times faster, right? So the rate of formation of hydrogen iodide is equal to 2 times the rate of decomposition of hydrogen gas. Right, because the rate of formation is twice as large for hydrogen iodide. And that's just due to the stoichiometric coefficient. And so that means that, and again, I'm going to substitute now what the rate of decomposition was, which was delta, which is just the triangle, delta H2 over delta t, and we have our 2 times in front of it, is equal to delta hi over delta t. And so this is just based off of the way that we're defining this right now, because it's the rate of decomposition. And so then the rate of decomposition is going to be delta H2, clean that up, delta T is equal to 1/2 change in concentration of hydrogen iodide over the change in time. Let me see if I can move this. Clean that up. And so now if we want to relate this to the overall reaction rate, what's the other thing that we have to consider? Right? What would not add up here? Or what wouldn't necessarily be equal to each other? There's just one thing that's off. If this is a reactant in this reaction, delta H2 is, what's the sign of this quantity going to be? Negative, right? So this is going to be negative. So for both of these to be related to the reaction rate, then now we just need a negative sign in here to make it a positive quantity. And that'll give us the relationship between the change in concentration with respect to time, the ratio of how things are being formed or decomposed based off the stoichiometric coefficient, and the reaction rate itself. So this will be 2 the reaction rate delta H2 is negative. So the reaction rate is going to be equal to minus delta concentration of H2 over the change of time. And then this is also equal to 1/2 the change in concentration of Hi over the change in time. And again, this comes from the balanced chemical equation. And so what this means is that if it's a product, it'll be a positive. We want you to include a negative sign. And you're going to be basically 1 over the stoichiometric coefficient of whatever that species is. And these two things are going to be equal to each other, and that gives you the overall rate of the reaction. Okay, any questions? Some people still writing.
It comes from the balanced chemical and electric.
Oh yeah, sorry, I abbreviated it, but this is equation. Sometimes I'll just write E, Q, N with a period after for equation. Okay, so why don't you guys take a second and see if you can express the reaction rate based off of each of the species in this arbitrary chemical equation, right? I say arbitrary just because A, B, C, and D don't represent, they aren't real molecules, they just represent any arbitrary molecule that could be there. So we're looking at the reaction rate. The reaction rate was defined as what again? We use the velocity speed analogy, right? The reaction rate is like the speed of the reaction, right? So it's how it's measured in units of what? Molarity over time, right? Molarity over time. And to calculate the reaction rate, we're concerned with two things. The one being the change of concentration of reactants and products. And what's the other thing we have to keep in mind with reaction rates? There's a change in concentration, and then what else? What else is given to you here in the problem that you need to use? Or what do we get from the balanced chemical equation here? Or what information does the chemical equation give us for looking at the reaction rate? Right. Change in concentration of reactants or products tells us the sign that's going to be in our expression. Is it going to be positive or is it going to be negative, right? What does the chemical equation give us? So for every, huh?
The like rate kind of like the.
It's related.
coefficients?
Yeah, right. That's exactly right. It was just the stoichiometric coefficients that are also important, right? Because that tells us the ratio of how things are being made or decomposed, right? So we need so 1, the change in concentration, and 2, the stoichiometric coefficients from the chemical equation. Right, so that's the information we're getting from the chemical equation, is we're getting the stoichiometric coefficients. The other thing we have to keep in track of is the change in the concentration. So here we're just writing an expression, right? We don't have any numbers, we're not plugging any numbers in, we just want to write an expression. But when we do have numbers, eventually, we do need to know how to write the expression to then use the numbers, right? Those are the two things when we're looking at next. What are we keeping track of there, right? So the reaction rate, which was represented by the large capital K, is then equal to, depending if it's a reactant or a product. So I'm going to write a long expression, and all of them are going to be equal to each other. So the first one is going to be for A, the second one will be for B, then C, and then D. So what is the reaction rate if we're expressing it, relating it to the concentration change of A, or the concentration of A? How would we write that? The first thing is a reactant or a product. Reactant, right? This is our reactant side, and these are product side, separated by the reaction arrow. So since it's reactant, what needs to be there? Negative sign, right? So it'll be negative. So we have the fact that it's a reactant covered now. And what else? What do we get from the chemical equation then? What did we get from that? The coefficient, right? And so how is the coefficient related to the reaction rate?
Free energy is to make 2C40.
Right? So that means that the reaction rate is going to be 1/3 of the change in concentration, or the rate of decomposition of A, right? So it's going to be 1/3 times, and again, it's units of what for the reaction rate? molarity per second, so that has to be a concentration on the top, the concentration of A over the change in time. And so that's all the reaction rate is expressed in terms of A here. Right, the change in concentration of A over the change in time. We divide it by 3 because we have to take away 3 A molecules for every time the reaction happens. It requires 3 of them. And the negative sign is there because the rate has to be a positive quantity and we're depleting A, right? The concentration of A is going down. So to make it a positive quantity, we have to include the negative sign. Okay. Does that make sense? Thumbs up, side, down. Okay. And what about for B? Negative.
Delta B.
Yep. Negative delta concentration of B over delta T, right? Because the stoichiometric coefficient is 1. 1 divided by 1 is still 1. So these are our reactants. And then our products, we have C. So since it's a product, do we need a negative sign? No, no negative sign, right? So this is going to be the change and the concentration of C over change in time. And what else do we need there? A 1 over 2, right? Because for each time this reaction happens, we're forming 2C. So the rate of formation of C is 2 times larger than the reaction rate here, because we create 2 of them every time that one reaction happens. And then similarly for D, the coefficient is 4 times the change in the rate of concentration of D over delta T. And I know these are kind of just abstract concepts right now because we're not plugging in any numbers or anything. We'll do that on the next problem. But this is how we would write an expression for the overall rate of the reaction based off of each species in this chemical equation. This is just a hypothetical reaction, right? Because A, B, C, and D aren't real molecules. The only thing that happens if you have a real chemical equation is you're just replacing A with whatever, maybe it's carbon monoxide or something, carbon dioxide. And so that's the only thing that changes, right? So this is the same fundamental idea in every type of problem of this nature. Okay, any questions on that? Okay. Is anyone still writing?
Can we go back to the previous slide?
Previous slide? Yeah, I'll go back. Is anyone still writing this one? Good, you're still good. Take your time. Good? Okay. All right. So consider this following reaction, right? So we have doesn't look like a balanced chemical reaction, but we have a reaction with some ions in it. This is probably a redox reaction. And it says for this reaction, we have peroxide reacting with iodide ion and 2 hydronium ions. And so in the first 10 seconds of this reaction, the concentration of I minus dropped from 1 molar to 0.868 molar. Calculate the average rate of the reaction in this time interval and determine the rate of change in concentration of H during this time interval. Right, so when I see this, so the average rate of this reaction, right, so there's some other words that were thrown in there that we haven't necessarily looked at yet. The average rate, if you have 2 data points, what's the average between those 2 points? Right, you just add them up and divide it by 2. Right, so whenever you see average rate when it's related to reaction rates, it's the same thing as just saying you have your 2 concentrations and then you have some interval that you're dividing it by. So the average rate over this time interval is just saying that we have delta concentration of I minus divided by delta T. Right, so average rate is just another way of saying the instantaneous rate or the slope at that time, the slope between those 2 points. Because really what we're doing is drawing a bunch of straight lines to represent the curve is kind of what's going on here. But that's the rate at that time between, 0, right? And that's another thing that these questions will kind of trick you with sometimes. It says in the first 10 seconds, right? So it doesn't give you a change in time, it just gives you a time value. But why would this potentially be equal to the change in time here? So you have an idea. So what I'm saying is, what is delta t? It should be 10 seconds, right? 10 seconds. That's because delta t is t final minus t initial. And what's the final time here? 10 seconds. And what's the initial time? 0, right? So that's why delta t is just equal to the time value that they give you here, right? So remember, we're always thinking in terms of changes in time in these time intervals, but here the way it's phrased is that time that they're giving you is actually equal to the time interval because the initial time is 0. Another thing people do in these types of experiments to kind of work around measuring a bunch of different time intervals is they just wait for the reaction to go to completion. And then you always know the final time minus the initial time is just going to be the final time minus 0. So that's how you can use your time interval for that. So you're going to calculate average rate, and then you have to determine what's the rate and change of concentration of H plus during this interval, right? So that means what is the change in concentration of H plus over 2, which means that you have to relate the average rate of I minus to the concentration per unit time change for H plus. And that'll be like what we did on the previous page. Those expressions are going to be related to each other. All right, so I'll give you like 5 minutes to kind of work through and see if you can do that. So you guys are obviously welcome to ask me. I'll come over, get you started, or you guys can talk amongst yourself. Maybe take this as a chance to introduce yourself to your neighbor, your friend, or future friend for the class. I'm going to go to the, hold on. What is our expression for reaction rate? And remember, I know there's going to be a lot of K's and E's and T's and stuff in the next couple weeks, but this is our reaction rate, right? That's how we defined it. Reaction rate. It was equal to plus or minus, depending on what product or reactant, and then it was 1 over the coefficient. And there's no real good way to write this expression, times the change in concentration over the change in time, right? So that's what you'll be using for the first part here, right? You need to calculate this reaction rate. All right, so for the rate, we have K is equal to, is it a reactant or a product, I minus? A reactant, which means you're going to put a minus sign there. What's the coefficient? 3, right? So 3, so we're going to have a 1 over 3. And then we have delta change in I minus over delta T. We can write this out in more detail. We'll have minus 1 over 3. What's delta I minus here? Mm-hmm. 0 point, what is it, 868 molar, right? We always want to make sure we include our units. That's how we know we're in the right place. Minus 1.000 molar, right? Because this is the concentration of I minus final minus the concentration of I minus initial, right? And you can put an I or a little 0, that means initial right there. And then what was the time interval? 10 seconds. And when you plug that all in, what did you guys get? So we'll have minus, and you said you got negative what? 0.004. 0.004. And because we have 2 negatives there, what happens with those? And this is in, what was the unit? What would be the units of this first, actually? Molarity over seconds, right? And if we double check our units, that's how we know we're also on the right track there. molarity over seconds, which is always the units of reaction rate. That all seems like it's checking out so far. And we know it needs to be positive, so we should end up with a positive quantity. And that's exactly what we get. We should get 0.004 molarity per second. So this is going to be our average reaction rate over this time interval. All right? Does that make sense? So I skipped one step in algebra here. I didn't write explicitly that, delta I is equal to I final minus I initial. And we see that we're taking a smaller number and subtracting a larger number because we're reducing the concentration of the species, which is why we know this is going to turn out negative. This has to be positive, which is why we added that other negative sign here, right? So all of our checks and balances are working right now. So that's how we get the average reaction rate. Okay, so that's our average reaction rate. The next part of the question is asking, determine the rate change in concentration of H plus during this time interval. And so rate change in concentration, that sounds like a funky expression. All this is asking you to solve for is delta H plus over delta T. It wants you to solve for that entire quantity. Right? It's still a change in concentration over time, which is why it's a rate change in concentration. And so how are we going to relate what we've already done to that quantity there? What can we relate to delta H plus over delta T? How are the concentration rates of formation and depletion or decomposition related to each other? It's kind of like they're all related to one thing, and then that's how they're related to each other. What are the rates of concentration change in water, I3, and 3I minus here? It's all related to. Right, if we went back to here. So these are all going to be, right, these are all the rate changes, and they're all related to the overall reaction rate, right? And so do we have the reaction rate in the problem? Have we solved for that at all? We solved for it in part A, right? So we solved for the reaction rate K here. And we know that K can be related to any of the rate change and concentration of any of the species here, right? And so we want to relate it to H plus. Right, so how would we relate it to H plus here? How is K related to the rate change, this quantity right here? Or another way of saying that is what's the expression of the rate in terms of hydronium or H plus?
1/2.
1/2 because it's a stoichiometric coefficient of 2. Is it a reactant or a product? Reactant. So it'll be minus. And then delta H plus over delta T. And so really, the only thing we're doing here is what variables do we have here? Or what are our two variables in this equation? We have, K. And then we also have this entire quantity, right? Because that's the thing that we're trying to solve for, is this delta H plus over delta T. And so K from the previous page we know is equal to 0.004 molar per second. We see this is still a change in concentration over change in time. So it's still going to be in units of molarity per second. And so to solve for this, all we have to do just multiply 2 to both sides. That 2 cancels out with that, and we can make it a -2, so that the negative sign cancels out as well. And that gives us delta change in concentration of H plus, or the rate change, is equal to minus 0.008 molarity per second. And so it worded it in a weird way just because it said the rate change in concentration of H plus during this time interval. But you could also ask this question another way just by saying, well, what is the change in concentration of H plus during this time interval too? And then you would just plug in 10 seconds for that and solve for delta H. Right, so the idea here was in the first step, we're solving for the rate of the reaction. Then once we have the rate of the reaction, we know that's related to each of the concentrations in this entire reaction. So once we have the rate of the reaction, we can use that to solve for the change in concentration of any individual species here in this reaction, because all of them can be expressed to be related to the rate of the overall reaction. Okay. Any other questions? No. Thumbs up, thumbs to the side, straightforward. Thumbs down. All right. So we'll end a little bit early today just so I can make sure to get